This conference will now be recorded.
All right, this is the 3A review, starting with number 13. We're finding the zeros of the given function, which means we're going to look at it and see if it's factorable first, and if not, then we would, of course, use the rational root theorem. This one looks like we can try to factor it, so we would factor out, they all have an x squared. That would leave me with x squared minus 4x minus 45. That's got a 1 in front of that, so we can try to factor this using just factors of 45, which are 1 and 45, 3 and 15, 5 and 9. Looks like 5 and 9 could work for us since it's a negative 45 overall, which means we need opposite signs. So this is going to factor into x squared times x minus 9 times x plus 5. You set each of those equal to 0 to find the zeros. So x squared equals 0 when x is 0. X minus 9 we would add over the 9. And x plus 5 we would subtract over, so negative 5. So my zeros are negative 5, 0, and 9. Okay. For number 14, we're listing the potential rational zeros of this function, which means we're looking for our P over Q list or C over D, depending on which textbook you learn this from. So C over D, I believe, is how we do it in our textbook. So that would be, this is the factors of your constant. This is the leading of coefficient. So C's factors are negative 18's factors are plus or minus, and I make my whole list plus or minus, 1, 2, 3, 6, 9, and 18. Those are all numbers that go into 18. And our D factor is 3, so plus or minus 1 and 3. So our C over D list of potential possible rational zeros is plus or minus, and then we have our long list, and you put each C over each D. So 1 over 1 is 1, 1 over 3 would be a third, 2 over 1 is 2, 2 over 3 is 2/3, 3 over 1 is 3. 3 over 3, though, is 1, which we've already listed. 6 over 1 is 6. 6 over 3 is 2, which we already have. 9 over 1 is 9. 9 over 3 is 3, which we already have. And 18 over 1 is 18, and 18 over 3 is 6, which we already have. So that is our comprehensive list. For number 15, they want us to find all the solutions of this equation, which means that if it doesn't factor, just by looking at it, we'll have to do the rational root theorem, and then we'll try to plug those into synthetic division or the remainder factor theorem, however you want to go about that, to determine one that goes evenly so that we can factor it down. The good news is you still have to do synthetic division no matter which way you choose to figure out which one is the root. But after you've done one round of this, you will be ready to factor using either factoring or the quadratic formula. So just depends on if the final quadratic is factorable or not. So the first thing you want to do is come up with your same list we did a minute ago. So C is 30. So factors of 30 are plus or minus 1, 2, 3, 5, 6, 10, 15, and 30. It's quite a list. Our D is 2, so our factors of 2 are 1 and 2. So the potential zeros that are rational that we're going to try are plus or minus 1 over 1, 1 over 2, 2 over 1, 2 over 2, which is 1, 3 over 1, 3 over 2, 5 over 1, 5 over 2, 6 over 1, 6 over 2, which is 3, 10 over 1, 10 over 2, which is 5, 15 over 1, 15 over 2, 30 over 1, and 30 over 2, which is 15. So this is our list. And remember, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of them, but plus or minus means it's really 24. So the best way to get started is to try 1 and -1 and hope that one of those works, but then at least you have kind of a guide of where to go from there. So this is 2. We're not missing any powers, no. So 2, -3, -17, and 30. We're doing synthetic division. I just find that's faster because if it works, you already have your factored pieces, essentially. So we bring down our 2 and we start multiplying. So that would be 2, add the column, that's -1. Multiply, then that would be -18. Multiply, that gives me a remainder of 12, so not 0. Then I'm going to try -1. 2, negative 3, negative 17, and 30 again. Bring down the 2. This is negative 2. That would be negative 5. That's going to be positive 5. That's negative 12. That's going to be positive 12. That's actually farther away from our goal than we want to be because 12 was closer to 0. So my gut instinct would tell me to try positive 2 next because that positive path got me a little closer to 0. So let's try 2. So 2, that would be 4. That would be 1. That's 2. That's negative 15 and negative 30. So yay, we found one that equals 0. So we know right away the solutions, we'd have our blank kind of on the test. One of the solutions is 2. Remember that this is actually tied to a factor of x minus 2, because if you solved it back over, it would be subtraction. So what you've really done is you've factored an x minus 2 out of this x to the third degree polynomial. And that leaves us with 1 degree less than we started with. So this is 2x squared plus x minus 15. And you can imagine that x minus 2 is kind of just out to the front. So it's been factored. So this is what this polynomial has been factored into. We need to solve the 2x squared plus x minus 15 because that is going to be our other two answers. They could factor, it could not factor, and then it could be a rational, irrational answer like square root of 3 can be involved, or it could even be imaginary. So since they said find all real solutions, if they end up being imaginary, we would only report x equals 2 as a solution. But I believe this might factor, so let's bring this over here. So 2x squared plus x minus 15 would be negative 30 when we multiply. And if we use a negative 5 and a positive 6, let's see if that factors. So 2x squared plus 6x minus 5x minus 15 equals 0. We can pull out a 2x, that would be x plus 3. Pull out a minus 5, that would be x plus 3. So we get x plus 3 and 2x minus 5. Set both of those equal to 0, you get negative 3, and that would be add 5 and then divide by 2. So our other two solutions to this x to the third power polynomial is negative 3 and 5/2. So there we go for that. So 16 is similar. We're going to be doing the same process again. So let's look at our C over D list. So C is plus or minus, it's going to be 33. So 1, 3, 11, and 33. D is 1, so it's just going to be plus or minus 1. So anytime your D is just 1, your list is just your C's. So it's plus or minus 1, 3, 11, and 33. So there's all 4 possibilities, but the plus or minus makes it 8. So let's try positive 1 first. That's going to be a 1, a negative 11, make sure no powers are missing, 35, and negative 33. Let's bring down the 1. That's negative 10. That makes that 25. And I believe that would be negative 8. Yes. So that is not a remainder of 0. Try negative 1. So that would be negative 1. That's negative 12. That's 12. That's going to be 47. That's negative 47. So see, this is getting way far away from where we want to be. So I'm going to try positive 3 next, since the positive got me closer to 0. So this would be 1 times that is 3. That's negative 8. That'd be negative 24. That's negative 11. No, positive 11, sorry. And then that is positive 33, which makes that 0. Yep, we found it. So this is, remember, this would kind of be a factor of x minus 3. And then this now would be 1 degree less, so x squared minus 8x plus 11. And we're going to try to factor that, which this does not factor. So yeah, because factors 11 are 11 and 1. So we're going to have to use quadratic formula. So we do know that one of our answers is 3 because of the one that worked for synthetic division. To solve this, I'm going to do x equals negative b plus or minus square root b squared minus 4ac all over 2a. So that's plus or minus the square root of 64 minus, what is that? 4 times 44, Looks like this one might be imaginary. That's 176. Oh, that was not 44. Sorry, I multiplied while I was writing it in the formula. It's 11. I'm glad I caught that. Okay, so this is 11 when you plug it in. When you multiply, you get 44. There we go. So that is 8 plus or minus the square root of 20 over 2. And square root of 20 is a 4 times a 5, so 2 square root of 5 over 2. So that's going to reduce to a 4 plus or minus square root of 5. So that's two solutions there, plus or minus. Okay, so that brings us to number 17. For this problem, all we're supposed to do is list all the information we can find about this rational function. So the way I usually start that off is I try to factor everything first, then we come up with our information that we need, okay? So if we look at the top, we can pull out a 3x on top. And that would leave me with an x minus 3. On the bottom, we can factor that into x minus 3 and x minus 7. That is going to reduce out and leave me with just 3x over x minus 7. Okay, so let's talk about x-intercepts. That's the first thing they want. The x-intercepts come from the numerator after you've reduced. So you set the part that's still got an x to it equal to 0, and that tells you your x-intercept. So that would just be 0. So we have an x-intercept at 0, 0. The y-intercept you find by plugging 0 either into the original or you can plug it into here. So 3 times 0 over 0 minus 7 is 0 over negative 7, which makes sense that it's going to be 0, 0 because that was also the x-intercept. The vertical asymptote is after you have reduced, anything left over in the denominator gives you a vertical asymptote. And remember, vertical asymptotes are not points, they're equations, so you solve it over. So x equals 7 is the vertical asymptote. Horizontal versus oblique, that has to do with your degrees. So the degree of the top is 1, the degree of the bottom is 1. If those degrees match, it's a horizontal asymptote, and it is the leading coefficient, so 3 over 1. That is also found by doing long division. You could say x goes into 3x how many times, and that would just be an answer of 3. If when doing long division you get just a number, it means it's a horizontal asymptote. If you get a number with an x on top of your long division, you have an oblique. So since we can only have one or the other, that means oblique would be none. And we do have a whole because this had a cancellation factor. So a whole is an ordered pair. So you set x minus 3 equal to 0 to figure out, because that's the part that canceled out. So that means the x coordinate is 3. You have to plug it into the reduced function to get the actual y value, because if you plug it into the original, you get zeros on top and bottom, and it doesn't make sense. So 3 times 3 over 3 minus 7 is 9 over negative 4. So it'd be negative 9/4. So there are all of my pieces, and this does not need to be graphed. Same thing for number 18. We're just going to go through and figure out all of the different pieces. I can pull an x out of the top first. That would leave me with x squared minus 7x plus 6, which I can factor again. That would be x times x minus 6, x minus 1. On the bottom here, I have x plus 9 and x minus 1. I'll bring that over. We have a cancellation here, so this is actually x squared minus 6x over x plus 9, or you can write it as x times x minus 6 over x plus 9. I like this version for the horizontal oblique situation, but this is easier for everything else. So anything left on top that is not canceled out is an x-intercept. So we need to set those equal to 0 to find our x-intercepts. So x equals 0 and x minus 6 equals 0. That means I have an x-intercept at 0, 0 and at positive 6, 0 when I solve that. For my y-intercept, I just need to plug in 0 for everything in the remaining reduced part. So 0 squared minus 6 times 0 over 0 plus 9, that's just 0 over 9. So that's also 0, 0. And that happens anytime the origin is also an x-intercept. Vertical asymptotes, that comes from just stuff left in the bottom. So x plus 9 is the only thing left in the bottom after we reduced. So that would be x equals negative 9 when we solve it. So that's our vertical asymptote. Horizontal versus oblique has to do with degree. If you were to do long division with this specific problem, notice that when you go to do it, x goes into x squared x times. That means, and I also need a constant here, so I'm going to put a plus 0. That means this is an oblique, not a horizontal, because there's an x up here. So we need to finish the long division to get the equation. So it's x squared plus 9x. We change our signs to do the long division. So that's negative 15x plus 0. X goes into negative 15x, negative 15 times. And once you've got your mx plus b, you don't need to do anything else. So this is an oblique at x minus 15, y equals. So it's that is the oblique asymptote, which means we have none for the horizontal. And then the last thing is whether or not we have a hole. So hang on just a second. For the hole, we need to look at what reduced out. So that was x minus 1, so that would be x equals 1. So that's the y value, or the x value for that. To get the y value, you plug it into the remaining piece. So 1 squared minus 6 times 1 over 1 plus 9. That is 1 minus 6 over 10, or negative 5 over 10, which is negative 1/2. Okay, so that is all of the pieces for that one. Now for 19, we're going to do the same thing, but we're actually going to graph the function. So these are a little bit easier. They don't have as much going on because we're going to make you actually graph it. So for this first one, you'd ask, does any of it factor? And the answer is no. Monomials don't factor, and this is not perfect squares or perfect cubes. So we're going to start right off with x-intercepts. And the x-intercepts is if something is still on top that has an x, you set it equal to 0. So 2x equals 0 means we have an x-intercept at 0, so 0, 0. The y-intercept you find by plugging 0 into all your x's, which will also be 0, 0. Vertical asymptote, there is something in the denominator that has an x. It doesn't cancel out, so we set x minus 3 equal to 0 and write the equation x equals 3. Horizontal versus oblique. This is a degree of 1 over a degree of 1, so the leading coefficients would be the horizontal asymptote. So that's 2 over 1, which is 2, which means we have none for oblique. And we do not actually have a hole since there is nothing that canceled out in this problem. So we're going to place down all the things we know on the graph, and then we're going to find some extra points to kind of fill in any missing pieces. So at positive 3, we're going to have a vertical asymptote. I like to do that in a different color on the video, so it pops out. At positive 2 on the y-axis, we're going to have a horizontal asymptote. I have an x and y-intercept that happen at the same point, which is 0, 0. Add some more marks on everything. And that's pretty much all we got from what we knew. So we need to pick, and the way I always break this up is I do a table, and I always let the x-intercepts and vertical asymptotes break up my number line. And I do that from left to right. So I had an x-intercept at 0, and I had a vertical asymptote at 3. So I'm going to pick something in each region of those. So I'm going to pick, and if I've already got a point on one side of my red line, I don't always do 2 in each region. Sometimes I'll just do 1. But when I don't have any points on a side, I'll do 2 or 3. So I'm going to pick -1, maybe, let's say 2, and let's do 2 on the other side of 3, so maybe 4 and 5. And we're going to plug them back into our original or reduced equation, depending on if you had anything that reduced. So that would be that, because it's 2x over x minus 3. So that's -2 over -4, which is 1/2. So we'll plot that point right there. And then 2 times 2 over 2 minus 3 is 4 over -1, so that's -4. So 2 and then down 4. And then we'll do 2 times 4 over 4 minus 3. That's 8 over 1, which is 8. So we'll need more marks for that one. 2, 3, 4, 5, 6, 7, 8. And then 2 times 5 over 5 minus 3 would be 10 over 2, which is 5. So 5 up 1, 2, 3, 4, 5. And if you even wanted to go a little further, you could do 6 to see the pattern. Now here's the interesting thing about rational functions. You can never cross the red line. That vertical asymptote, you can't cross it. So we know for a fact that this guy is headed down towards this red line, but never crossing it. And this one is heading up and never crossing. We don't know so much always about the blue line, the horizontal asymptote, or the oblique. We don't know for sure if it's crossing that or not. There's a way to test this really quick so you can know. All you have to do is set your function. This is just so you can have peace of mind, equal to the actual asymptote you got for either your horizontal or your oblique. And if you cross multiply and solve that, one of two things will happen. Either all the x's will cancel out when we go to solve, or you'll have an x left over. If you have an x left over and you can solve for it, then you actually cross that blue line at that specific value. So this is 2x equals 2x minus 6. Notice as soon as you move the 2x's over, you get 0 equals negative 6. So that means we don't cross our horizontal. So that's just a nifty way to check that for yourself. So that means that we know that this is going down towards the blue line because it's heading in the same direction it was going, but it doesn't cross it. And this one's heading up towards the blue line, but doesn't ever cross it. And excuse my crude drawings, they're the best I can do without any graph grid. So for 20, we're going to do the same thing and graph that one. And then all we have left on this video is the inverse functions. So let's do factoring first. So there is an x plus 2 and an x minus 2 in the denominator because of the perfect squares. Our x-intercepts, there are actually none because there are no x's on top. For the y-intercept, you would set all the x's equal to 0. So this would be 4 over 0 squared minus 4, which is going to be negative 1. So 0, negative 1. We get a vertical asymptote. We actually get 2 because both of them are in the denominator and they don't cancel out. So x at negative 2 and x at positive 2. And that comes from solving each one individually equal to 0. Horizontal versus oblique. This is a degree that is smaller on top than bottom. So if you try to do the long division here, you would ask, can x squared go into 4 with no x? And the answer to that is no. So when you say no, you're actually saying it goes in 0 times, which is a number. So that's a horizontal asymptote, and that means we don't have an oblique. So anytime the degree of the top is smaller, the asymptote is always y equals 0. And then holes, there were none because there was nothing that canceled out. So none. Okay, so let's graph what we know. Okay, so we have a vertical asymptote at negative 2 on the x-axis. And we have another one at positive 2. And we have a horizontal asymptote of y equals 0. So that is the x-axis. And then we have a y-intercept point of 0, negative 1. So that's right about here. Okay. So it looks like there's making 6 regions here by the black and the red separation. So it looks like we're down in this bottom region here. But to be sure, I could set my original function or my reduced function equal to the horizontal asymptote and try to solve. If you cross multiply that, you get 4 equals 0, which doesn't make sense. There's no x's left, so we never cross. So we know this blue point is stuck down here forever. But we're going to actually plot some points to get some other information. So we're going to plot at least 2 points in between each of our vertical asymptotes because we don't have any x-intercepts. So negative 2 and 2 are my vertical asymptotes. Maybe I'll do negative 3 and negative 4. Negative 1 and 1 because I already know that 0 is here, and we'll do maybe 3 and 4. Okay, so go back to your original. 4 over negative 4 squared minus 4 is 4 over 16 minus 4, which is 4 over 12, which is 1/3. Okay, 4 over negative 3 squared minus 4 is 4 over 9 minus 4, which is 4/5. So that's a little bit bigger. Negative 1, so 4 over negative 1 squared minus 4 is 4 over 1 minus 4, which is negative 4/3. So that's a negative. You'll get the same answer for positive 1 because when you plug it in, you're still squaring the 1, and it'll be 1 minus 4 on the bottom. And you're going to get symmetry here as well. So since I don't have a lot of room, you can try these out on your calculator. You get the same answers you did before. So negative 4 is at 1/3. So that's about right here. Negative 3 is at 4/5. That's a little higher. So since we already know this doesn't cross any of its asymptotes, this is going to go towards the red and towards the black line. Negative 1 is at negative 4/3. Positive 1 is also at negative 4/3. So this guy is actually going to go towards the two red ones and almost look like a parabola. We don't know for sure if this is the highest point, but we're just doing a general sketch. And then 3 4/5 and 4 1/3. So this is going to have a symmetry to that other side. And excuse my graphs, they should be getting closer to the black line. But there is the rough sketch for that. Okay, the last 3 questions on the review for the test are all about inverse functions. Inverse functions only exist when your function is 1-to-1 or has been restricted so that it is 1-to-1 on its domain. And the way we find them is you kind of think of that as being y, because f of x and g of x really are just symbol notation for y. And we swap x and y and we resolve for y. Or some people will do it as solve for x and then swap x and y. The gist of it is essentially the same because you are solving for the other variable and you swap x and y so that it becomes the inverse function, because an inverse just takes an ordered pair 1, 2 and switches it to the ordered pair 2, 1. So I usually just solve this for, I do the swap first. That's kind of how I approach it. So this would be x equals 3y plus 6, and then I solve for y again. So I'm resolving now. So that would be that, and then x minus 6 divided by 3 equals y. Some people like to break that up. It's 1/3 x minus 2, make it linear, essentially. And then we don't call it y anymore. We call it f inverse or g inverse, which in this case it would be g inverse. So that would be the answer to that one. And it's also okay, as long as your teacher has no problems with that, as leaving it x minus 6 over 3. Okay, so let's find the inverse of a different function. This one's a little bit more involved. So I'm going to remember that f of x is really the letter y. I'm going to swap x and y, so this would be x equals y minus 3 to the 5th minus 2. And now I want to get y by itself, so I'm going to add 2 over. I need to take a 5th root of each side to get rid of this 5th power. So that's the 5th root of x plus 2 equals y minus 3. And I'll need to add over the 3. So I get y equals the 5th root of x plus 2. And then notice the plus 3 is not under the root. It is added after we took the root. So this would be f inverse of x. Now for the very last one, we're going to do the same concept, except it has 2 x's. So then when we solve it, you have to worry about, you're going to have 2 y's that you're going to have to get together, essentially. And then we're going to talk about the domain and range, because the domain and range is just, remember, swapped. So if I look at this first as kind of the letter y, and I do my swap first, this would be x equals 5y plus 4 over 3y minus 7. You can't solve for y if there's 2 of them and one's on top and one's on bottom, so we kind of cross multiply to clear that out. So 3xy minus 7x, that's distributing x to both of these, equals 5y times 1 plus 4 times 1. Your goal is to get the y's together, so we're actually going to move all the y's to one side, and we're going to move anything that's not a y to the other side. So this will be 3xy minus 5y equals, that would add over and be 7x plus 4. You can now factor out a y that they have in common on the left side. So that's 3x minus 5. So that got us down to 1y. That was the key here. And then we divide it. So y equals 7x plus 4 over 3x minus 5. And then we're going to write that using inverse notation. So h inverse of x is 7x plus 4 over 3x minus 5. So there is my function notation. Okay, so the domain and range has to do with, first of all, you just need to know the domain of both functions because they're inverses, their ranges just are the swap of the domains. So this guy is undefined when 3x minus 7 equals 0. So that would be add 7, divide by 3. So x cannot equal 7/3. This one, we'd set the 3x minus 5 equal to 0. So that's 3x equals 5, or x cannot equal 5/3, because that would make us divide by 0 in that one. So here's the thing. Range is going to be a y cannot equal, because it's not an x anymore. And since this domain is 7/3, this range is, you have to restrict 7/3. And since this domain is 5/3 is restricted, this range has 5/3 restricted. If you remember what we just did with rational functions, that is the horizontal asymptote for these, because these are rational functions. So this one has a degree of 1/1. Notice it has 5/3 as its horizontal asymptote. And this one has 7/3 as its horizontal asymptote because it also has matching degrees on top and bottom. All right, so that's it for the video. Hopefully this helps you guys, and good luck on your exams.